Okay. Your programming test number 2. I already announced the preliminary information. You can check the dates and time. It should be very consistent. You can check it on the e-class. I'm going to release the detailed guide, but that one wouldn't put too much new information, just about the format for the test, which would be just the same as programming test 1. The example questions have been posted, and also the solution. Give a try, and then look at the solution. If you want me to go over any parts with you, reach out to me earlier. And then assignment number 3, the solution also has been released. You can also take a look. Might be a different way of solving the problem. You can learn from that. Again, reach out to me if you want any guidance on that. Written test and also programming test 1, result and feedback released. If you want to go over any part of it, again, reach out. The makeup lecture, which will be covered in the final exam in April, but it doesn't hurt to really start earlier. There are many interesting ideas over there, especially circular array. Okay. And those template, office hour, and TA content. I still got 3 p.m. today if you want to speak to me this week. Any questions about the course? All right, let's now do recap as usual. So last time we finished the last bit about binary search. Specifically, we spoke about how we can trace the binary search Java code that we spoke about. The main thing you guys want to pay attention to is about once you call the recursive helper method for the binary search, you're basically using the from and to, the 2 numbers on the 2 ends to specify the search space. And you're going to have the search space each time if you decide to go to either the right or go to the left, right, and etc. That's really the essence for binary search. That's why it actually has log-n performance ultimately, which is much better than linear search. And we try to do this very important exercise over here. In order for us to figure out the running time for recursive algorithm, we will have to, number 1, to formulate, based on the Java code we are given, formulate that into recurrence relation. And the recurrence relation, usually we just use a letter T to specify the running time. And then you got different input sizes. It could be empty, it could be size 1. So these 2 are the base cases. Usually it will just be constant amount of time. And then you got input size n, in which case you have to look into very carefully about how you actually make the recursive call. And before you make the recursive call, you might have some certain preprocessing you have to do, sometimes post-processing as well. So that's something we'll see. Okay? Preprocessing and sometimes post-processing, and you want to see exactly what it is. And for example, here, preprocessing for binary search will just be constant amount of time. And then we're making the recursive call either way. We don't really do both, right? That's also something you want to pay attention to. And once you got a recurrence relation, how do you figure out the running time? We're doing something kind of a very naive, but it will actually work for the purpose of this course. To solve the recurrence relation, you can simply keep applying the definition for size n in general until you can see the pattern. And the goal is we really want to reach out to base case. And you want to see the pattern and see how we can reach out to the base case. And for the details, you guys can look through the recording. I managed to record it from the evening class on Tuesday. It's the same stuff. You can take a look and review that. And today, we're going to do one more unfolding today. That one is going to be even more challenging, which is nice to do that together in the class. The pattern definitely requires a little bit more insight into math to really discover that. But it's not too bad, right? We'll take a look together very soon. All right, and we talk about MergeSort. This is really the 3rd sorting algorithm we're talking about in the course. We talk about selection sort, we'll talk about insertion sort, and MergeSort, there we go. And I'm going to talk about quick sort as well after the MergeSort. And this is the conceptual idea. It's really about split and merge. It keeps splitting until you reach the point that, sorry, let me say it again. You split into 2 halves, and then you recursively try to sort each half. Once you get a sorted half, you're going to merge them together. And the merge routine turns out to be the most expensive routine you have to use for every recursive call at every level, basically. Okay? And when we get to the running time, you also see exactly how that work is going to be contributing to the final running time. That's something we'll see today. And this is a Java implementation for MergeSort, and the source code is already on the lecture site. Take a look. And then I think the most important part you want to really recall is, number 1, the recursive case over here, all the steps over here really correspond to what we describe visually right here. They correspond to exactly that, right? So somehow things will just work magically. Well, there's no magic. Of course, behind the scene, you have to really check how things work together. And the merge method here, right? As I said, in assignment number 2, you actually did it already. So it's a nice preview. It was intentional. I want you guys to try to implement the merge yourself in the assignment before we actually talk about it. The most important conclusion is as follows. The merge routine or the merge method here, the running time is going to correspond to the size of the left half plus the size of the right half. This is a very important conclusion because as we try to observe the running time in the recursion tree, this is going to be needed, right? So I'm assuming that you're going to go over about why the running time will end up being the sum of the sizes of the two halves, right? That's something you get a review from last time. And we did this tracing here about the merge sort, right? You basically keep splitting until they reach the base case where each list is already sorted because each list of size 1 is automatically sorted. And you're going to merge all the way bottom up back to the root. And eventually, you will get the sorted list right here. All right. There's one insight I want you guys to see right away. Okay. You want to see something like this. Think about split. So split. Let's think about how many splits is really necessary for us to see to really reach the base case. Well, let's go top down. We start with the list size 1, 2, 3, 4, 5, 6, 7, 8. All right. We start with the size 8. After the first split, we actually got 2 lists of size 4 and 4. And then after the second split, we actually got 2, 2, 2, and 2. After the third one, we got 1, 1, all the way to 1. 8 of them, right? That's the split we got to do. How many? We got exactly 1, 2, and 3, which is log n. This one tells us the height of the recursion tree that we're building has the minimum height possible, which is log n. If you try to relate this height over here to the bounds that we talk about in the binary tree lecture, right? It's really connected over there. Okay, so let me say here. The number of splits is really the minimum heights, which is log n. Right? It's a very important insight, log n. That's the first thing I want to point out today. Log n, the number of split. And once we get back to the bottom level, once we get to the bottom level, so now it's time to return from the recursion, right? Think about what would be the cost for the merge. As we said, for each merge, the cost will be the sum of the sizes of the left and right. So the cost for all the merge over here is going to correspond to number of elements in here. Agree? Okay, how many? 1, 2, 3, 4, 5, 6, 7, 8. Exactly n. All right. So I'm going to put right here about the merge cost. So I'm going to put here, right? The merge cost, okay, right here. At the bottom level here, I got exactly 1, 2, 3, 4, 5, 6, 7, 8. 8. What about the second last level? Still, I got 2 plus 2 plus 2 plus 2. Also 8, also n. Again, this one here, 4 plus 4, 8, also n. This one tells me every level of merge is going to cost linear time. How many levels do I have? Log n. Do the math and log n. That's how you can understand about the runtime for MergeSort intuitively. All right, let me repeat once more. When you look back to this tracing over here, you got to look at 2 things. Number 1, how many splits do you need in order to split the original list of size n all the way to just 1? It's going to be log n, number 1. Number 2, for each level from the bottom up, the number of the cost for the merges you got to do will just correspond to the sum of the sizes for each list. And it's just turned out to be just n throughout. So if you do the multiplication, each level is going to cost n. How many level? Log n level, so n log n. Right? That's one way to informally kind of visually justify the running time for MergeSort. Okay? So let me just say one more thing. And each level costs n. Okay? So you really want to pay attention to these two numbers. We got log n splits, and each merge is going to take linear time. All right. Of course, to really justify this formally, we got to do the recurrence relation in just one moment. Okay. All right. Any question? We good? All right. So let's now figure out the recurrence relation. Okay. Okay. Let's now go to over here, the running time. So this diagram here basically just summarizes what I just said, right? A little bit in a more general way. So how many split do you need in total? The height of the tree is going to be log n, right? Exactly over here, right? Let me just mention again. So the log n over here corresponds to the number of splits you have to do. From n all the way down to the base case 1. And then the n over here corresponds to the cost for each. So the cost for the merges for each level. At each level. If you multiply these two numbers together, it's going to be n log n. That's MergeSort. Very beautiful distribution, about the very balanced, I should say. All right, so let's now talk about recurrence relation. So we want to figure out these three input cases, right? We got 0, we got 1, we got n over here, right? Let's start with the simple one. If the list is simply just empty, right? So this will correspond to right here. If the size of the list is empty, it's automatically sorted. That one there, you can safely just put t of 0 is simply just 1. Okay, constant. You just create an empty list and return it, right? So I can put 1 here. Okay. And then what about if the list is actually of size 1? Not too bad. It's still constant. You just got to create a list of size 1 and then return it. That one wouldn't be more than constant. Okay. So t of size 1 will be also 1 right here. Okay, 1 and 1 so far. Let's talk about recursive case. Okay. The only recursive call we are making is right here. This is the only recursive call. Okay? So you can see we got sorted left and sorted right. That one there is not difficult to understand because we are using the middle part over here, right? The middle index, basically. Where's the middle? So think about if this is the original list, let's say. Okay, just illustrate it to you. Let's say this is the list I'm given right here, right? That's the input I'm given. And then the middle is just about right here in the middle, right? Middle. And then this will be the left, and this will be the right. And roughly, this will be n over 2. This will be n over 2. Okay. So, and then we actually have to sort them. Oh, I beg your pardon. I said something completely wrong. Okay, let me take it back. This merge, of course, we're going to merge the two lists, but there are two recursive calls. Okay, again, I apologize. I simply didn't mean to say that. So we actually make two recursive calls. You can see the first one here is sort on the left, right here. And the second one here is sort on the right. All right, so these are the two recursive calls, right? Each one of them. So compare this with a binary search. In a binary search, we either go to the left or go to the right. But here, you got to do both. So it's different, right? So you can think about the left is right here, and the left and also the right. Each one of them is simply n over 2. So think about this is something we can assume to be some running time for a list of size n over 2. And this one here as well. Like how we did it for binary search. N over 2. Right? We're going to count both. Right? So these are the two recursive calls. Right? And when you split, we assume that the sublist method here in ArrayList is simply constant time. We assume that. It's very efficient operation. And then we get to the merge right here. All right? The merge. And we can really use the useful result we derived from last time. Right? What's the running time right here? Right? I'll put it here. Okay, for the merge over here, the running time for that is going to be the size of the sorted left plus the size of the sorted right. Right? Each one of them is simply n over 2. It's going to be just n. Okay, you can see big O of n, right? So that's why it is so important when I recap last time's lecture, you have to remember how we derive the running time for the merge being the sizes of the two lists being merged, right? Okay, so for this one here, you can think about, let me just split them. Okay, this part here. Okay, this part here, you can think about it's more like a preprocessing, which is a splitting. This one here would be big O of 1, right? We assume it's a very efficient operation. On the other hand, this one here is not that efficient. You have to go over the two lists, right? This one here is going to be big O of n in the worst case. And now we gotta count them up together, all right? So the recursive case right here, so for the else part, this will be the else part over here. It will be something we're gonna add up together, okay? So think about we got 1 here, and also we got n over here. Think about the 1 is like a pre-processing before the recursive call. And the merge here is more like a post-processing, right? Pre and post, okay? You can see very clearly. 1 plus n, and then you can say plus the 2 recursive call, okay? So we got t of m divided by 2 and t of n divided by 2. 2 times, basically. 2 times t of n divided by 2, okay? I'm just trying to show to you how to count them together. And we are now ready to put this down, okay? It's going to be, you can think about t of n divided by 2 plus t of n divided by 2, and then plus n. You can simply drop the 1. It's not going to impact anything. We'll just keep the n. That's something we're going to make sure we kind of count that or consider that properly when we try to unfold. And of course, for this one here, it would be very convenient if we can simply say it is 2 times t of n divided by 2. Equivalent. Okay. So what we have done here is the second time we are given a piece of Java code, and then we try to formulate the running time for the piece of given Java code into recurrence relation, in which you have to consider 3 different cases. 2 base cases, empty, and also like a singleton list, and then the general case. That's usually the pattern. Okay. All right, any question? Spence.
Yeah, sorry, so why did we drop the 1 here, but we kept it in
Yeah, it's because, good question. Because right here, you can see the n, think about anything other than the recursive call. In this case, if you got n plus 1, you know that n is going to dominate over 1. So we don't really need to consider both. You can still put the 1 into the unfolding process. Just for simplicity, I can just drop it safely. But in the case of binary search, you just got a recursive call t of n divided by 2 plus 1. So the only non-recursive operation is 1, so you cannot drop it. Okay, that's why. Good question. How about this? Keep the highest power for the non-recursive call. Yeah. All right, this will be the fun part. Okay. I can tell you guys, this one here is going to be kind of a look confusing for the first time, but we'll do some warm up, and then we'll do some. I'll give you guys a moment to really think about what the pattern might be, and then we'll do it all together from scratch. Okay, it's not too bad, but definitely more challenging than what we should do for binary search. All right, let's now do the warm up first. Okay, warm up. So we got t of n. What if n happens to be n divided by 2, half size? This means I'm going to replace every occurrence of n, 2 occurrences, right, by 2, n divided by 2, n divided by 2, n divided by 2. Watch out here, okay? Very careful. All right, let's see what that should be. That one will be 2 times t of n divided by 2, and then divided by 2. Plus what? N? N divided by 2. Okay, watch out. Okay, because when I was doing this exercise for the first time, I made that mistake. Hopefully you wouldn't do that, right? It should be n divided by 2. Okay, be careful. Okay. So we basically got these occurrences for n divided by 2, right here, and right here, right here. Okay. And of course, you can simplify that if you wish. This one will be n divided by 4. All right, if you're comfortable about this warm-up exercise here, you kind of get for each individual step you have to do for the unfolding. That's a good sign. All right, let's now try to do it. We'll start with the general case, T of n. T of n equals, by definition, 2 times T of n divided by 2 plus n. And what we do is we try to unfold the first time. We're going to see what this is exactly by applying this definition, replacing every occurrence of n over here by n divided by 2, n divided by 2, n divided by 2, which we just did in the warm-up. All right, let's now write it out. So this is what I want to do. All right, 2 times something over here. And don't forget we got a plus n, right? This is something I'm going to unfold. And that one there, we know it should be 2 times T of n divided by 4 plus n divided by 2. I'll pause for one moment to make sure everybody's comfortable. Okay? Now, if you're taking notes, do one more step before I write it out. So what you should do is, you should really try to see if I try to unfold one more step for T of n divided by 4, what should the next one be? Okay, 30 seconds. And then I'll write it out. You might have already been able to see the pattern already, but just bear with me one more step. I would say typically you just need about 1 or 2 unfolding steps. I would say 2 would be safer. You definitely don't need more than 3. That'll be too many. You don't need that. All right. So I got 2 times and then 2 times over here. This is the part I want to do, but let's now copy the rest from before. All right. So what I need to do is this part over here. All right. What should that part be? Well, that one there is going to be 2 times T of n divided by 8 plus what? Yeah, good. Thank you. There we go. That's enough. Things get a bit more complicated, right? If you try to do more unfolding steps, you might just end up confusing yourself. So I think that's enough. And let's see what the goal is. The goal really is we want to keep doing this until we can reach the base case. And usually, the base case you may want to find will be maybe the 1 case, because that will fit more nicely whenever you want to have log, or maybe you want to have some binary nature. But of course, if you think a 0 is also worth considering, go ahead. There might be more than one way to do the unfolding. But for now, let's say our goal is to reach the base case right here. We want to figure out how many unfolding steps should we really do so that we can reach the T of 1. Okay, so I'm going to write T of 1 here first. And that one there, I know itself, by definition, is simply just 1, right? But the problem is, I got so many complicated stuff right here. How do I generalize them? That's my issue, if you agree, right? So there should be 1 plus some very complicated stuff right here that we're going to figure out. So how do we figure it out? You have to identify the pattern. Okay? I would suggest, I'll give you some hints, just another 30 seconds. You can give it a try if you want to. If you only look at these, it's not as easy. It's doable. I'm not saying it's not doable. It might be as unnecessarily complicated for you to see the pattern. But why don't you try to simplify this line here, and also try to simplify this line here. I'm pretty sure you can do. If you try to simplify each line, then you will be able to see the pattern easily. Okay, I'll give you guys maybe 30 seconds, not too long, and then I will also guide you through. But just give it a try. Okay. Okay, just one moment. Okay, let's take a look. This one here, we don't need to simplify any further. That's pretty much it. But we might be able to distribute the times 2 somehow. Okay, it's actually, there's a nice pattern here. So let me help you with that. Would you agree, first of all, if you see the 2 over here, that can cancel out this 2 here. Agree? Because 2 times n over 2 should really give you n. All right, that's one thing. And then if you look at, for example, 2 times 2 can also cancel out. Oh, sorry, 2 times 2. Oh, I shouldn't do that. Beg your pardon? No. What am I doing? That'll be enough, okay? So let me say it again. You got 2 times here, and then you can cancel this out. That'll be enough. And then 2 times 2 itself just 4. All right? So what I can write alternatively is this, okay? This one here can be rewritten as 4 times t of n over 4 plus 2n. Why 2n? N here, and also 2 times n over 2, which will be n plus n. If you have any doubts, you may want to look at the math more closely. All right? So that's a nice simplification that will allow you to see the pattern much more easily. But I would suggest we do one more. Okay? How do we simplify this guy over here? Right? Are we able to do something like how we did it before? Are we able to cancel this out? Are we able to cancel this out? It seems like we can, right? Okay. So for example, you can see that over here, I got the 2 over here that can definitely cancel this out. Okay, and then I got the 2 here and the 2 here. It can definitely be used to cancel this out. Right? And then, of course, I cannot do this, right? You cannot do that. And but 2 times 2 times 2, which will be 8, 8 times t of n over 8. Right? So the simplification should be something like this. It should be 8 times t of n divided by 8, and then plus 3n. Why 3n? N here with this cancel out, and n here with this one cancel out, right? Exactly 3n. Now we should be in a good position to see the pattern. Are you able to see it? Somehow? Much easier, I can tell you. All right. Let's now try to rewrite some denominator. This guy here is 2 to the power of 1. This guy here is 2 to the power of 2. And this one here is 2 to the power of 3. And if you don't mind, let me do one more. Let's say this one here is, of course, 2 to the power of 1. This one here is 2 to the power of 2. And this one here is 2 to the power of 3. All right? Yeah, I'm pretty sure you can see that, right? I'll just tell everybody, right? It's quite obvious now. Okay? Of course, to really kind of rewrite different terms for you to see the pattern, that's a critical step that you're gonna do by yourself, right? Okay, what's the pattern? So if you look at the exponent here, 1, that tells you you got some multiplicative constant here, 2 to the power of 1. And also you got exactly 1 plus n. Exactly 1 instance of plus n, just 1 instance. On the other hand, you see here, you got exponent being 2. That means you also got the multiplicative constant 2 to the power of the same thing. And then how many plus n do you have? 2, right? Exactly 2 here. All right, one more, just to verify. You can see here, the exponent is 3. You got 2 to the power of 3 and also 3n. That's the pattern. All right, so now how do you apply this pattern over here to this line over here, right? So there are 2 things. We're going to write it down, okay? Oh, let me move this a bit right here. So this T of 1, you can think about this T of 1 is like this T of n divided by a little bit like that. Okay, I'm going to rewrite it in a moment. Something is going to come before that, multiplicative constant, and something is going to come after. The one that should come before that should be 2 to the power of something. And also plus something times n. What's that something? That something should be the denominator written as 2 to the power of something. All right, hopefully you can see, all right? Now, how do we rewrite it to see that exponent? Let's now rewrite it. So let's look at the 1 right here. Okay? 1 here is simply equal to n divided by n. Isn't this familiar? We did something very similar last time for binary search. Agree? Okay. So that one is equal to n divided by 2 to the power of something. What's that something? Log n. All right, that's something we said last time. Okay. So you can, once we figure out this exponent here, like figure out this 3 here, everything else can be filled in accordingly. Okay. So this will just be equal to n over 2 to the power of log n. All right. So now I can simply say log n. That's not a okay. Log n over here is going to correspond to this guy here and this guy here. All right. Let's now do one more step. It is going to be equal to 2 to the power of log n times t of 1 is 1 plus log n times n. Right? And then this one here we know pretty well is simply n, which will be equal to n plus n log n. And apparently this is higher term asymptotically. So you can drop this. So what's the running time for MergeSort? N log n. All right. So it should be big O of n log n. Okay, so that's a conclusion. You can see this one here can go very badly when you try to unfold or try to see the pattern. If you only try to see the pattern based on, let's say, this and this, it's going to take a long time. You might just get very confused. But as you can see, once you try to simplify each line, it's actually much easier. I wouldn't say that's easy, just easier. Okay. All right, any question about this one here? All good? All right, so we are done with the MergeSort over here. And then you really want to review the high-level idea about the Java code and also the tracing and also the running time, right? We cover many things about the sorting. Okay, okay, we're done with the MergeSort. No follow-up question? We all good? Good. Let's now talk about another sorting algorithm, quicksort. Okay, for the quicksort, MergeSort, we are done with it completely. You guys can also take a look at the running time analysis, which is pretty much what I just said, right? Just more textual form. Recurrence relation, and that's the process that we just did all together. Okay, quicksort. So we are really solving the same computational problem about sorting, just the same problem. So we cannot assume anything about a structure or organization of the input sequence or input array. How do we do it in the quicksort? I will again start with some general idea about a quicksort before I show you the Java code. Okay, let's now build this from scratch, and then I can mention also some very important insights about the quicksort. Even though it's called quicksort, if you somehow run into the worst case for the quicksort, it's not that quick. You can still go into quadratic. I'm telling you the conclusion right away. So for the quicksort, there's a very critical step, which is called pivot selection, which I'll mention that individually. If you choose the pivot correctly or ideally, you will get n log n, just like a MergeSort. But if you choose the pivot in a way that's going to make the follow-up steps so expensive, it's still going to be just like a selection sort, insertion sort. You're not benefiting from quicksort. Okay, so that's something I want to mention up front. Okay, Let's now start with this, okay? So let's now mention about the different steps for quicksort. If you recall, in the merge sort, we got split and merge. In a quicksort, I would like you to think about there are three main steps you have to worry about, right? I'll mention them here. One is called pivot selection. Okay, pivot is a keyword. Pivot, okay? And then we have also something called partition. And then we got concatenation. So these are the three critical steps for quicksort. And what's going to determine about the overall running time, whether you go for the very quick sort, like an n log n, or go to the very slow sort, like an n square, it really depends on the pivot selection. Okay, I'm going to talk about it. Okay, let's say for now, I would just choose a pivot, always the last element. I always choose the last element in the array to be the pivot, which will be very efficient for me to choose, just array indexing, let's say. Let's say we assume that we always pick always select pivot being the last elements. Okay, let's say that's always the case. But I'm going to talk about the insight into pivot selection in just one moment. Okay, so what we're given is we're given some array that's completely unsorted. Once you have picked the pivot, you're going to do something called partition. And partition is like this. Imagine that, oh, just one moment. Imagine that you're going to put this pivot over here in the middle. And then you're going to scan through the rest of the array. Anything that is smaller than the pivot, you put it on the left. Anything that's larger than the pivot, you put it on the right. But these do not need to be sorted. You just got to make sure every element in the left should be less than the pivot. Every element in the right needs to be larger than the pivot. But individually, the left and right don't need to be sorted. Okay? So what you will do is you're going to have the left over here. And also, you're going to get the right over here. Everything on the left is going to be strictly less than the pivot. Everything that's on the right should be strictly larger. However, let me emphasize, these two do not need to be sorted. Left and right are still unsorted. All right, so now I can talk about the critical step about pivot, right? Can you always guarantee? Well, the way I draw that, by the way, I'm saying that roughly you got about n/2 element that's smaller than the pivot. And also, I got roughly about n/2 element that's larger than the pivot. Can that always be the case in general? It will only be the case if the pivot happen to be what? This is something you guys learned maybe from 2030, not EECS, math. When you learn about statistics, there is some measure of a group of number. Somehow, if you choose that number there, then about half of the number will be smaller than that. About half of the number will be larger than that. What is that? Mean? Average? Median or average? Guys, median or average? Median. Okay, good. Not average. Average, not necessarily. All right, let's review some math. How about that? Okay. This is really important. Okay, I'm talking about all the important stuff, right? If that's not relevant, I wouldn't even bother you. Pivot selection, ideally, the median. Why average may not be a good idea in general? If your data happen to be skewed towards the low end or high end, the average may not be exactly in the middle. So what do I mean? I'll just draw that conceptually, okay? So let's say you got some sequence of number over here, and also you got another sequence of number over here, right? Median guarantees it's going to be exactly in the middle, right? This will be the median, okay? So this part here, I would just say median here. If your data are roughly spread out quite evenly, in that way, the average will be very close to the median, right? I'm pretty sure you know that, right? So average will be around the median. So that's how I would draw that, okay? Average here, if the data points spread out evenly somehow, more or less. On the other hand, the average could be very much maybe close to the high end if you got many high numbers, for example, right? So we call this kind of data point skewered, maybe towards the left, towards the high end or the low end. So the average distance from, I'll just continue from here, right? Distance from the median if the data skewered, right? So that's why choosing the median is very important. By choosing the average, it can be risky depending on the distribution of the data. But if you can, if you somehow you're sure about certain assumption about where the average is, you might be okay. But in general, you should really choose the median. That's my point. Okay. And I want to mention one more thing. What would be the most efficient way? Well, naively, how would you? Let's say you give it an array. How would you choose the median? Naively. Well, presumably, you can sort the array and then just go to the middle index in the sorted array, right? But that one is going to be very costly, wouldn't it? If you use a MergeSort, let's say, to sort the input array and then get a sorted array and then go to the middle one, it's going to be n log n. If you apply the insertion sort on the input array and find the median, it's going to be n squared, right? However, for your knowledge, there is certain very quick algorithm for finding the median, which is beyond the scope of this course. But I can assume there's such a thing, okay? For your information, it's called median of medians algorithm. Median of medians algorithm. That one there is able to find the median in big O of n time. We don't really cover this particular algorithm in this course, but for your knowledge, just know that there is an efficient way to really find the median in linear time. You don't really need to sort the array first. You don't have to. You can get away from that. Okay? For those of you who might be interested, you can feel free to research on that. Okay? Okay, so that's about the pivot selection, which is extremely important. It's going to be the dominating step for the most inferential step for your quick sort. All right, let's now continue. So once we choose the pivot, we're going to do the partition. So now we got a left, we got a right, but this is not sorted yet. This is also not sorted yet. So pretty much like a MergeSort. We're going to sort the left half. We're going to sort the right half. All right. Next one, we're going to do recursion. So we're going to recur on left and right. And by the way, individually, this is not sorted, and also this is not sorted, not yet. So what we'll do is, there's something I forgot to annotate in the beginning. So think about our job is to sort the entire array, right? That's our job. That's the original input. And now what we do is we're going to sort the left, and also we're going to sort the right over here. right? So this one will be the left, where every element is smaller than the pivot. And also, we're going to sort the right, where every element is guaranteed to be larger than, because we did a partition previously, right? And once we have done, so of course, when we first do the sort, they are not sorted. Once the recursion return, each one of them is going to be sorted, okay? Now, and then we'll discuss. Once this is returned, so it's going to results are sorted left and right. Let me write it down. And we also got here. And don't forget, we also got a pivot, right? Don't forget. Okay. Okay, so this is the left, and this is the right. What will be the next step? You might be thinking, why don't we do a merge? Because the left is guaranteed to be sorted, the right is also guaranteed to be sorted. Why don't we just merge them? Is that what you're thinking? If you're thinking that way, you're missing the very important insight into quicksort. Is a merge necessary? If you don't think that's necessary, why not? Anybody? Let me put it here, just before I point to you. Okay, so here's a critical question. Is merging the sorted left and the sorted right necessary? By the way, it's not wrong if you try to merge it, but it's just unnecessary. And the hints will be, think about how the partition was done. That's a hint. Spence, go ahead.
Yep, because in our merge algorithm, we had to sort them again.
No, actually, merge, remember, merge is not recursive. Merge is like a method where you simply got some sorted list, you got another sorted list. They're both sorted. I can merge them to get a bigger sorted list. Right? But now I'm asking, is it really necessary? Yeah?
Each time you put the pivot into place, it's going to be in place in the entire array. So like by the time you get to the bottom, you don't...
Not quite. Not quite. Oh, I'll take one more, and then we should really, okay, I'll give you the answer. Go ahead.
Well, isn't the left and right side, like, the left story smaller than the right side, so there's no point in...
Yeah, exactly right. So I deliberately didn't really write this property again, right? Remember, everything on the left is guaranteed to be smaller than the pivot. And everything on the right is also guaranteed to be larger than the pivot. So if I know that this sorted sequence has all the element less than the pivot, and this sorted sequence has all the element larger than the pivot, why don't I just concatenate them together? I don't need to merge. All right? That's something you will see even more explicitly when we try to trace this quicksort. All right? That's something you want to keep in mind. No, not necessary. All right, so the final step is something we call concatenation. That's why you can see the step here, I said concatenation. I didn't say merge. Okay? So what we do is we're going to do a final concatenation. Concatenation simply means, so far we got the pivot value and two individual sequences. We're just going to join them together to be a large sequence. And that one there is not that expensive. Okay? Okay, so what I'll do that explicitly here. By the way, individually, this is sorted. This is also sorted, right? So what I will do is I'm going to just paste that right here. Okay, I'll make it a little bit smaller. Even smaller. There we go. All right, so that'll be a final step. In which case, in which case, we're going to join the three parts together into a larger sequence. Join that here, and also join that here. Okay, this one here is a final sorted sequence that we have, right? Let me recap. Choose the pivot, partition, call to recursive call, and then you don't need to do merge, you just concatenate. That's quicksort. But the performance for the quicksort all depends on how the pivot has been chosen. If the pivot is very close to the median, you should be good. But if somehow it's very far away from the median, you might get something very close to quadratic, n squared. Okay? All right, any question? All right, why don't we take a very short break by taking attendance, and then we'll continue. Okay, so we already learned about the general idea about quicksort. So the next step will be, let's now talk a little bit about Java code, which is not as difficult because we don't have any merge. So the concatenation and also partition, they're very easy to follow. I don't need to mention too many details. You can definitely look at the Java code. And then I'm just going to run one example together with you to see what the partition will look like. Right? And then we're going to talk about some tracing. We're going to do it together so you guys a little bit more intuitive view about how the quicksort should work. And then we'll talk about recurrence relation. We wouldn't try to solve the recurrence relation anymore, but I want to talk about best case versus worst case. Okay? So that'll be the remaining part for quicksort. And if we have time left, hopefully we can talk a little bit about binary search tree before next Tuesday. Okay, so let's see the Java code, right? We got a sort method here, and that one there is recursive. You can see that we got a sort right here, and we call the recursion twice, just like the merge sort on the left. Again, you guys really want to look at each step over here that corresponds to exactly the visual summary I made earlier before the break, right? That's something I'll leave to you. And the pivot value, let me talk about once more. So here, just for convenience, I always choose the last elements in the list, right? But let me emphasize again, right here, I'm hoping that the one I choose always is going to be close to the median. Of course, it cannot be true always, but for the example I showed to you, they happen to be the case, all right? Ideally, this is close to the index of median. But in general, this cannot be true. Let me emphasize that, right? And let me just mention one more time. In order for you to choose a median properly, so there is an algorithm called median of medians. Okay, let me mention one more time. Median of medians. Algorithm. That one there is going to give you linear time. You don't need to do any sorting. Okay? As opposed to sort and select. Actually, for sort and select, it's something you have done. Do you know where? Assignment 3. Remember assignment number 3, the first task? Many of you try to somehow traverse the tree, sort it, and then go over the array. Pretty much like that. So what's the running time for that? If you do the sorting, maybe most likely if you do selection sort, insertion sort, that'll be n squared. All right? Anyway, I want to get a little bit more connection to it. All right? If you don't know what I'm talking about, never mind. Okay? Well, you should mind for next week. So you better follow up with assignment number 3. Okay? So about choosing the pivot, right? So that one there is basically just constant time, all right? So here, I'm just being lazy, so that's constant time. But in general, you should really spend a linear time of work, like a median of medians to get a true median. All right, let me talk briefly about these two methods. I gave you the Java code about partition all the element less than or equal to the pivot, and also all the element larger than the pivot is more like a 1022, 1021 level question task. So I wouldn't bother you with the detail. You guys can take a look at the method here and make sure you know how to do it. All right. Basically, you will see less than or equal to the pivot value and also larger than the pivot value, right? You can see exactly how that can be done. Let's just run one example here. Let's say if I choose the pivot to be the last element at index 7, all right? So let's say this is a pivot. That means everything that's less than the pivot should really go to the left. Anything that's less than 50 and anything that's larger than 50 should really go there. And don't include the pivot, of course. All right. 85 should go to here. 24 should go to here. 63 should go to here. 45 should go to here. And 17 should go to here. 31 should go to here. 96 should go to here. Right? Obviously, it's a linear time algorithm because you got to scan through the entire array, except for the pivot, which is n minus 1, which is linear. Right? And one thing to see, you can see that after the partition, left is not necessarily sorted. And also the right is also not necessarily sorted, which is what I mentioned before the break. Now you can see more concretely, right? Okay, so left and right, you can say not sorted yet. Okay, and then when you try to do these two, they are more or less big O of n, linear time, right? You got to scan through the array. And when you do the sorting over here, well, we're going to do the recurrence relation pretty soon, right? So these two will just be, so here's a question here. Let's say the original problem here, the list. If I want to figure out its running time, which will be T of n, right? You might be thinking, maybe quick sort just like a merge sort. I would say, if I want to sort the left, it will be T of n divided by 2. And this one here will be T of n divided by 2. Would that always be the case, though? Here's the thing. For quick sort, not necessarily. It will only be the case that you got exactly roughly n divided by 2 for left and right if the pivot happened to be the median. I'll show you one example where the way you choose a pivot is so bad, you just end up having almost like a selection sort. I'll show you that, okay? So that's why I want to point it out over here. So think about these two will only be your best case if, only if the pivot is roughly about the median. If it's not the median, no chance. You're going to get very bad performance for quicksort, even though we implement that. All right, so this part over here is just about concatenation. All right, concatenation, you just call the add all method from the array list, which you will assume to be very cheap operation. So this part is more like a post-processing. All right, that's about concatenation. Concatenation, big O of just 1. All right. All right, the various part. So there's really not much to really go over for quicksort. You just got to remember the different stages about choosing the pivot and also partition and also sort individually and then concatenation. Right? Just remember we don't really need to merge. Okay. Any question about the Java code here? Yeah.
Let's say we were using primitive arrays, then how would you do the concatenation? Would it like?
Yeah, I know. So if you use the array, I agree with you. In that way, concatenation may not be that efficient because you may have to use a loop to really copy, right? So that's why you may want to use a link structure for a quicksort, maybe. Yeah. Mm-hmm. Good insight. Good. That's kind of the informed decision you have to make when you think about, let's say, once you graduate from this course, should you use array or should you use linked list for some algorithm, right? That's exactly the right decision, right? All right, let's now trace it very quickly, okay? So here I'm demonstrating to you, even though I have a very bad strategy about choosing the pivot, which I don't even care about where the median, what the median is. I always choose the last one, but I'm lucky this time. I can always happen to be choosing the median. Okay, so I'm going to choose the last element here as the pivot. Okay, always. So 50 here is the pivot. Imagine that 50 is here. Imagine, all right, and then I'm going to partition that into 2 halves. Left half should be strictly less than 50, and then right half should be strictly larger than 50, assuming that there's no duplicate. Okay. And 85 should go to here. 24 should go to here. 63. And then 45 17, 31, and then 96. Okay? If I miss anything, please tell me. Okay? So you can see we got the left and the right. Roughly 4 versus 3, about half. Pretty good, roughly. Okay? What we do is we gotta try to run a quick sort again, recursively on this, recursively on this. The first step for the quick sort is gonna be choose a pivot and choose a pivot. Always choose the last one. Okay? So I'm going to choose 31 as a pivot, and also 96 as a pivot. Okay? So let's say we imagine 31 is here, imagine that 96 is here. Okay? 24 should go here, 45 should go here, and 17 should go here. And 85 should go here, and 63 should go here. And imagine that this part here is just empty. Nothing. There's not a number that's bigger than pivot, which is completely fine. So roughly 2 versus 1, still about half and half, so we're still fine. Okay. All right, so this is already the base case. It's already sorted, so we don't need to recur any further. But this one here is larger than 1. It's too big. So let's now do quick sort recursively again. So you're going to choose a pivot, which is 17. Imagine that 17 is in the middle. All right? So 24 should go to here. There's nothing there that's less than 17. All right? And then for here, we're going to choose the pivot, 63. Imagine that 63 is in the middle, so only 85 will go. Right? All good. Now we have done with all the partitioning. Right? And we should really return from the recursion. So what we do is we got to go do concatenation. As I said, we don't need merge. All we got to do is take the left sequence, concatenate it with the pivot, concatenate it with the right sequence. That will be it. It's guaranteed to be sorted. Okay. So if you try to do the if you try to do the concatenation here, there we go. Okay, you can try to do concatenation. It's more like you got the empty sequence right here, concatenated with the pivot, concatenated with 24. That one there is going to give you 17 and 24. So this part here is now sorted. 17 and 24, right? So this now is sorted. And then, if I back up, how about the concatenation here, right? So this one is sorted, also this one is sorted. So what I do is I can say 17, 24 plus the pivot, which is 31, plus the 45, right? And I'm guaranteed to get a sorted sequence. So that one there is going to give me 17, 24, and then 31 and 45, right? Hopefully you can kind of see how exactly that works, right? Concatenation. And then for this one here, I can do this half as well. Okay, so this one very quickly. This one here, I'm going to concatenate empty right here, plus 63 plus 85. That one is going to give me a sorted sequence here, which would be 63 and 85. Okay, so that one there is also sorted right here. Okay, and then I'm going to do concat at this level. And this concatenation is going to be 63, 85 plus 96 plus the empty. And that one there is going to give me 63, 85, and 96. Right? So now I got this one sorted and also this one sorted. So final step, I'm going to concatenate this sorted, pivot, and right sorted. Right? There's no merge. I don't need it. Because everything here guaranteed to be less than this. Everything here guaranteed to be larger than that. So that's the beauty about the property of partition, really. Okay, let's do it a final time. So I'm just going to do a final partition. Okay, which will be partition this together with this. Oh, sorry. Concatenate this one here plus this one, right? That's simply just going to be 17, 24, 31, 45, right? And the pivot is 50. And then I got 63, 85, and then 96. Right? So this will be the final sequence. And this will be considered as the best case for the quicksort algorithm, simply because the number, recall this. When I actually look at the tracing for MergeSort in the beginning of today, I mentioned about how many splits did you have to do for MergeSort, log n. So the best case for the quicksort is the number of partition you will have to do is also log n. However, you might have chosen a very bad pivot, in which case the number of partition you got to do will be linear, which I'm going to show to you, right? That's the final story I got to tell you. Okay, I'll put it here. So the best case for the number of partitions, which will correspond to the height of the tree, right? You can look at the tree over here. What's the minimum for the height of the tree for binary tree? Log n, right? Log n partition you got to do. And then for each level, you're basically going to do the actually put things to the left of the pivot and to the right of the pivot. That's also going to take linear. That's something we'll see a little bit later. Okay. All right. Any question about tracing here for quicksort? Good. All right. Let's now do some discussion here. We wouldn't solve any more recurrence relation. Don't worry. But we're going to do something like just to formulate the running time. I'm going to talk about worst case versus best case for a quicksort. Okay. For MergeSort, it's guaranteed to be n log n, but MergeSort could be a little bit more difficult to implement because you got to make sure the merge actually works, the pattern actually works. But for quicksort, it's rather easy to implement. But you got to make sure you really choose the right pivot. It's the key. All right, let's talk about running time. Okay. To start with, you can see that this part here is rather straightforward about the list being either empty or of size 1, just like a MergeSort, right? I can simply say 1 and 1. That was easy, right? We don't need to repeat the details. And also, for the best case, will just be the same. The base case wouldn't really matter. Okay, so this one here, I can also say 1 and 1, which is base case. All right. And then, let me give you one example where the pivot I choose is so bad. All right, let's see. Let's say I got an input sequence here, 9, 7, 5, 3, and 1. And I will use the same strategy to choose the last element as a pivot. Okay? This will be the pivot. Okay? Let's think about if this is the pivot, I'm going to put everything less than that to the left. Is there anything less than that? No. Everything is actually larger than that. In that way, I'm actually going to get 9, 7, 5, and 3. So that's one partition. All right? And then I'm going to choose another pivot, which will be, again, the last element, the consistent strategy. And then I'm going to put everything that's larger than 3, anything that's less than 3 to the left. Is there anything less than 3? Also, no. Everything is larger than that. In that way, I'm going to put 9, 7, and 5. Okay. Similarly, you can see the pattern here. I choose 5 here. Everything is larger than that. I got 9 and 7. And then I'm going to choose a final pivot here, which will be 7. And everything is actually larger than that. I'm going to put 9 here. How many partitions have I done? All right, if you think about it, partition 1, 2, 3, and 4. The size of the input is 1, 2, 3, 4, 5, about n minus 1. Pretty bad. Okay? N minus 1, which is big O of n. This one really gives you the insight that if you have the strategy of choosing the pivot that's so bad, so far away from the actual median value, the number of partitions you're going to do will be big O of n. But at every level, you still got to do the big O of n work to do the to do other stuff. So you would get n squared. Okay. So what I need to emphasize here, now the overall running time is big O of n squared. That's the overall. Okay? It's simply because if you look at every level here, especially look at this one here. These ones, as we mentioned earlier, this one here is going to be big O of n. Okay? And then the left and right are not balanced. That's why it requires big O of n partition to really get down to the base cases. Okay? Roughly speaking, you can think about if you have a very bad pivot, the size of the left is going to be about big O of 1. And the size of the right is going to be about big O of n, roughly speaking, the size. Sizes of partition. That's going to give you the worst case running time. Okay. And if you think about the big O of n squared here, you are not really better off. It's just like selection sort or insertion sort. All right, any question here? Good. Yeah, Nathan, just before I ask you a question. Okay, let's now complete this one here very quickly. Okay, so T of n. So it turns out if you got very bad partition over here, that means, for example, one of them is going to be very close to linear and one of them is going to be very close to constant. So you can think about, for example, this one here could be T of, for example, just about n minus 1, which is n, roughly. And the other one there will be very close to constant, which you can just ignore. Roughly about T of 1, okay? Which is the base case anyway. And so the recurrence relation is going to be something like T of n minus 1, or you can say T of n, doesn't matter, plus the n. The n here is really about the partition you have to do right here. Okay? One more thing to mention before I get to Nathan. Okay. If you choose the right pivot right here using the median of medians algorithm, it's not going to increase any overhead because that one there is guaranteed to be linear, in which case it's just going to be linear as well. Because this part here is going to be linear no matter what. So doing anything additional as linear is not going to impact overall running time. Okay? So if you want to use a median of medians algorithm in your quick sort, you can feel free. Okay? It's not going to make the performance worse. Yeah, go ahead.
So when comparing this to the MergeSort,
Yeah.
is the in terms of runtime, like primitive operation runtime, which one's more effective?
The runtime, you mean overall runtime for these two?
Like given they're both in their
Merge sort doesn't matter best or worst case. It's going to be n log n always. It's not possible to implement the merge sort and you got n squared. On the other hand, for the quick sort, if you have chosen the pivot wisely, close to the median, then you will get n log n. But if you choose the median so badly, it's so far away from the median, you might get n squared. Yeah. All right? Yeah.
So under the assumption that we have a correctly chosen pivot, how are they going to perform?
Sorry?
Under the assumption that we've chosen our pivot correctly, like how would they perform?
You mean for quick sort? Yeah, so okay, assuming that for the quick sort you have chosen the right pivot that's so close to the median, then merge sort, quick sort will perform just the same. But quick sort may be a little bit easier to implement. Conceptually, you don't need to do anything like a merge, right? Yeah. All right, so let's talk about the best case, which is really n log n. So for the best case, I just want to emphasize for the best case, for the recurrence relation, we're just going to get just like a merge sort. 2 times T of n divided by 2. I'll explain that in a moment. And then plus n. The n here, again, is just about the partition steps. No way around. you have to do a linear scan to really see which one should be less than the pivot and which one should be larger than the pivot, right? It will be big of n. And then if you're reaching the best case, that means for the left and the right, they will be very balanced in terms of their sizes. Okay, so this will be T of n divided by 2, T of n divided by 2. Okay, just give me 2 minutes and then we're done. Okay, we can just finish this nicely today. So the best case would be if you actually got your input here, and if the strategy is like this, if I can really happen to choose the median, that means I'm going to get a left half over here and the pivot and also the right half over here. They'll be roughly equal size. That will be the best case. Okay. So this will be roughly big O of n divided by 2, big O of n divided by 2, the size of the partition. All right. Okay, let me use 1 minute to tell you what you should do beyond this, right? What you should do is you want to take the best case recurrence relation, solve it, and make sure it is n squared. Okay, so this one here will turn out to be big O of n squared. Oh, sorry, I beg your pardon. N log n, what am I saying? N log n, that's a best case. Just like merge sort. Just like merge sort. So if you solve this recurrence relation, you will just get the same answer. And then if you try to solve this one here, which we haven't really done, you'll get n squared. That's the worst case running time. All right, any question? All right, so next week, we only got one lecture next week since you got programming test on Thursday. So next Tuesday, we'll start a topic about binary search tree. All right, see you next week.